Hello friends, welcome to the lecture on critical points and paths of nonlinear systems. So, in this lecture we shall consider a real autonomous system which is nonlinear. Say for example, dx by dt equal to px by dy dt equal to qx by. Now, suppose this system has an isolated critical point 0 0, further px by and qx by are such that px by is equal to ax plus by plus p1 x by, qx by equal to cx plus dy plus q1 x by, where a, b, c and d are real constants and they satisfy the condition that ad minus bc is not equal to 0. For the functions p1 x by and q1 x by, we have the following condition. P1 x by and q1 x by have continuous first order partial derivatives for all x by and are such that p1 x by over under root x square plus by square as x by tends to 0 0 goes to 0 0, and q1 x by over under root x square plus by square as x by goes to 0 0 also goes to 0. As so p1 x by and q1 x by satisfy these conditions, then the system 1 can be written as dx by dt equal to ax plus by plus p1 x by, dy by dt equal to cx plus dy plus q1 x by, where a, b, c, d, p1 x by, q1 x by satisfy the conditions 1 and 2, that is ad minus bc is not equal to 0, p1 x by and q1 x by have first order continuous partial derivatives, and p1 x by over under root x square plus by square, q1 x by over under root x square plus by square tend to 0 0 as x by goes to 0 0. Now, if px by and qx by in the system 1 can be expanded in the power series about the point 0 0, then we can write the system 1 as dx by dt equal to p 0 0 plus partial derivative of p with respect to x at 0 0 into x, partial derivative of p with respect to y at 0 0 into y, and then second order terms. So, a12 into x square, a22 into x by, a21 into y square, and then higher order terms, and similarly dy over dt can be written as q 0 0 plus partial derivative of q with respect to x at 0 0 into x, partial derivative of q with respect to y at 0 0 into y, and then second order terms and so on. So, b12 into x square, b22 into xy plus b21 by square and so on. Now, since 0 0 is a critical point of the nonlinear system, we are so px by and qx by at 0 0 must vanish, and so therefore p 0 and 0 and q 0 0 is equal to 0, and then this system, okay, this system is of the form 2. This system is of the form 2, where a is partial derivative of p with respect to x at 0 0, b is partial derivative of p with respect to y at 0 0, c is partial derivative of q with respect to x at 0 0, and d is partial derivative of q with respect to y at 0 0. p1 x by is a series of terms a12 x square plus a22 x by plus a21 by square and higher degree terms, and q1 x by is b12 x square plus b22 x by plus b21 by square and higher degree terms in x and by. Now, we can see that p1 x by and q1 x by over under root if we divide p1 x by under root x square plus by square and q1 x by under root x square plus by square, then as x by goes to 0 0 they go to 0. So, here a, b, c, d are this, ad minus bc therefore is not 0 provided this Jacobian is not 0. We know that the Jacobian of pq with respect to x y is of this form, be defined like this. Okay, so a is partial derivative. So, a is partial derivative of x with respect to partial derivative of p with respect to x at 0 0. Similarly, b, c and d, and ad minus bc is not equal to 0 means that this Jacobian is not 0. So, the requirement this is clearly met, because P1 x y and Q1 x y contains second and higher order terms. So, when we divide by under root x square plus y square and take the limit as x y tends to 0 0, the limit becomes 0. So, this requirement is met and this requirement is also met. Now, let us consider the system dx by dt equal to x plus 2y plus x square, dy by dt equal to minus 3x minus 4y plus 2y square. You can see that here a is equal to 1, b is equal to 2, a is equal to 1, b is equal to 2, c is equal to minus 3 and d equal to minus 4. And so, 1, 2, minus 3, minus 4, a, b, c, d. Okay. So, this is minus 4 and then plus 6 is equal to 2. So, a d minus b c is not equal to 0. Okay. So, our nonlinear system is such that the coefficients of x y, that is a b in the first equation, c d in the second equation, satisfy the condition a d minus b c not equal to 0. P1 x y is equal to x square, Q1 x y equal to 2y square. Since P1 x y and Q1 x y are polynomials in x and y of degree 2, okay, they have continuous first order partial derivatives, and further P1 x y over under root x square plus y square. Let us find the limit of this as x y tends to 0 0. We shall show that this limit is 0. So, this is limit x y tends to 0 0 x square over under root x square plus y square. Now, we know that in order to find this limit, okay, we go by epsilon delta definition. So, in order to show that this limit is 0, let us begin with an epsilon which is positive number. So, let epsilon greater than 0 be arbitrary. Then we have to find a delta greater than 0 such that mod of x square over under root x square plus y square minus 0 can be made less than epsilon whenever under root x square plus y square is greater than 0, but less than delta. So, this is equal to x square upon under root x square plus y square. Now, this I can write as under root x square plus y square, because x square plus y square is under root this is less than or equal to actually you see mod of x is equal to under root x square plus y square, okay, and x square when x is real is equal to mod of x square. So, x square is equal to so this is less than or equal to mod of x is less than or equal to under root x square plus y square, and x square is mod of x square. So, this is what this is nothing but x square upon under root x square plus y square is equal to mod of x square upon under root x square plus y square, and mod of x is less than or equal to under root x square plus y square. So, under root x square plus y square divided by under root x square plus y square. So, what you get is under root x square plus y square. So, this is this, and this is less than delta, okay, this is less than delta, and delta is less than or equal to epsilon. So, what we do is let epsilon be greater than 0, then mod of under x square upon under root x square plus y square minus 0 can be made less than epsilon whenever 0 is less than under root x square plus y square less than delta, and delta is to be chosen. So, less than or equal to epsilon. So, there exists 0 less than delta less than or equal to epsilon such that mod of this is less than 0. So, this implies that limit of x square upon under root x square plus y square as x y tends to 0 0 is equal to 0. So, in a similar manner we can show that limit x y tends to 0 0 q1 x y over under root x square plus y square, which is equal to limit x y tends to 0 0 q1 x y is equal to 2 y square upon under root x square plus y square. We can show that this is also 0. So, p1 x y and q1 x y satisfy the condition 2, that is they have continuous first order partial derivatives, and p1 x y over under root x square plus y square goes to 0 as x y goes to 0 0, and q1 x y over under root x square plus y square also goes to 0 as x y goes to 0 0. Now, from the requirement 2 on p1 x y and q1 x y that they tend to 0, p1 x y over q1 x y divided by under root x square plus y square tend to 0 as x y tends to 0 0, it means that they tend to 0 more rapidly than the linear terms ax plus by and cx plus dy. Hence, we suspect that the behavior of the paths of the system 2, this system non-linear system 2 could be similar to that of the paths of the related linear system dx by dt equal to ax plus by, dy by dt equal to cx plus dy, which is obtained from the system 2 by neglecting the non-linear terms, and in general it turns out that this is actually true. Let us discuss this theorem. Consider the non-linear system 2 where a b c d p1 and q1 satisfy the requirements 1 and 2 above, that is ad minus bc is not equal to 0, p1 x y and q1 x y have continuous first order partial derivatives, p1 x y over under root x square plus y square and q1 x y over under root x square plus y square tend to 0 as x y tends to 0 0. So, consider also the corresponding linear system 3, this system 3. Then both the systems have an isolated critical point at 0 0. Let us take let us consider the characteristic equation lambda square minus a plus d into lambda plus ad minus bc equal to 0, and let us say that lambda 1 and lambda 2 are its roots. Then it turns out that the critical point 0 0 of the non-linear system 2 is of the same type as that of the linear system 3 in the following cases. If lambda 1 and lambda 2 are real, unequal and are of the same sign, then the critical point 0 0 is a node. We know that for the linear system 3, if lambda 1 and lambda 2 are real, unequal and are of the same sign, then the critical point 0 0 is a node, and same is true for the non-linear system. So, if lambda 1 and lambda 2 are real, unequal and of the same sign, then the critical point 0 0 is a node. If lambda 1 lambda 2 are real, unequal and are of opposite signs, then the critical point 0 0 is a saddle point. So, in the case of non-linear system also, if lambda 1 and lambda 2 are real, unequal and are of opposite signs, then the critical point 0 0 will be a saddle point. Same is the nature as for the linear system here also in the case of non-linear system. If lambda 1 and lambda 2 are conjugate complex, but not purely imaginary, then the critical point 0 0 is a spiral point. If lambda 1 and lambda 2 are real and equal and the system 3 is not such that, okay, system 3 means again let us see, the system 3 is the corresponding linear system, this one. So, if it is not of this type, a equal to d not equal to 0 and b equal to c equal to 0. We have discussed this situation in the case of a linear system. There were two possibilities. One possibility that in the case of real and equal roots was that a equal to d not equal to 0 and b equal to c equal to 0, and the other case that we had discussed was in the case of all other possibilities which lead to equal roots which are real. Okay, we had discussed the type of the critical point. So, here if lambda 1 and lambda 2 are real and equal and the system associated linear system is not such that a equal to d not equal to 0 and b equal to c equal to 0, then the critical point 0 0 is a node of the non-linear system. Now, the critical point 0 0 of the system 2, that is the non-linear system, is not necessarily of the. So, here there is a difference between the type of the critical point in the case of non-linear system and the associated linear system. The critical point 0 0 of the nonlinear system is not necessarily of the same type as that of the linear system 3 in the following cases. If lambda 1 and lambda 2 are real and equal, and the system is such that A equal to D not equal to 0 and B equal to C equal to 0, then although 0 0 is a node of 3, it may be either a node or a spiral point of the nonlinear system. If lambda 1 and lambda 2 are purely imaginary, then although 0 0 is a center of 3, it may be either a center or a spiral point of the nonlinear system. Now, let us look at this remark. Although the type of the critical point 0 0 is the same for 2 as it is for 3 in the cases 1 to 4 in the above theorem, 1 2 3 4 in this theorem, the actual appearance of the paths may be somewhat different. For example, the figure 1 shows a typical saddle point for a linear system. You can see this is this 0 0 here is a saddle point for the linear system. Here also 0 0 is a saddle point, but the appearance of the saddle point is are the paths, okay, is different. They are not linear, they are curves, non-rectilinear paths. So, the figure 1 shows a typical saddle point for a linear system, whereas figure 2 suggests how a non-linear saddle point might look. A certain amount of distortion is clearly present in the latter figure, in the figure 2, but nevertheless the qualitative features of the two configurations are the same. So, we can see here we have two half line paths, one half line path here, they all enter and approach 0 0 as t goes to plus infinity, and then we have other two half line paths, they also enter and approach 0 0, but this is the half line path for t tends to infinity, these two are the half line paths for t tends to minus infinity, and these are the non-rectilinear paths which are asymptotic to one of the four half line paths. And here we do not have half line paths, we have rectilinear paths which enter and approach 0 0. You can see here there is one non-rectilinear path and there is another non-rectilinear path which enter and approach 0 0 as t goes to plus infinity and t goes to minus infinity, and these non-rectilinear paths are asymptotic to these half line paths, these non-rectilinear paths which approach enter 0 0. So, actual appearance of the saddle point here in the case of nonlinear system may be somewhat different. Now, we discuss the stability of the critical point 0 0 of the nonlinear system 2. If the critical point 0 0 of the nonlinear, if the system linear system 3 is asymptotically stable, see we have the nonlinear system dx by dt equal to ax plus by plus p1 x by dy by dt equal to cx plus dy plus q1 xy. The associated linear system we are considering is dx by dt equal to ax plus by and dy by dt equal to cx plus dy. So, if the critical point of the linear system is asymptotically stable, then the critical point 0 0 of the nonlinear system is also asymptotically stable. Now, here are the exceptions. If the roots lambda 1 and lambda 2 are purely imaginary, if the roots lambda 1 lambda 2 of the constructive equation are purely imaginary, then although 0 0 is a stable point of the linear system, it is it may be asymptotically stable but not asymptotically stable, or an unstable point, critical point for the corresponding nonlinear system. If either lambda 1 or lambda 2 is real and positive, or they are conjugate complex with positive real parts, then not only 0 0 is an unstable point of the linear system, but also 0 0 is an unstable critical point of the nonlinear system 2. So, let us consider example 1. We see that, let us go to the example 1. So, this is example 1, dx by dt equal to x plus b 2y plus x square, dy by dt is minus 3x minus 4y plus 2y square. So, let us consider the type of the critical point 0 0 here. So, let us write the corresponding linear system. dx by dt equal to x plus 2y, dy by dt equal to minus 3x minus 4y. So, the eigenvalues here are lambda square minus a plus d. So, a is 1, d is minus 4. So, minus 3 into lambda plus a d minus b c, which is 2 equal to 0. So, lambda square plus 3 lambda. So, lambda plus 1 into lambda plus 2 equal to 0. So, the eigenvalues are minus 1 and minus 2. Okay, now let us see what is the type of the critical point at 0 0. Let us go to this theorem. It says that the critical point 0 0 of the nonlinear system 2 is of the same type as that of the linear system 3 in the following cases. If lambda 1 lambda 2 are real, unequal and of opposite signs, then the critical point 0 0 is a saddle point. Oh sorry, we have to go to 1. If lambda 1 lambda 2 are real, unequal and of the same signs, then the critical point is a node. So, here the roots are minus 1 and minus 2, which are real, unequal and have the same sign. So, the critical point 0 0 is a node. So, the roots are real, unequal and of the same sign, the critical point 0 0 is a node. Now, we have to go to the stability of this. If the critical point 0 0 of 3 is asymptotically stable, then it is also 2 is also the critical point 0 0 of 2 is also asymptotically stable. So, let us see in the case of this regarding stability, we know that the eigenvalues are lambda 1 lambda equal to minus 1 and lambda equal to minus 2. So, it is a asymptotically stable critical point of the linear system. Dx by dt equal to ax plus b by dy by dt equal to cx plus dy, and so this is also 0 0 is also asymptotically stable point in the case of the nonlinear system of example 1. So, the critical point 0 0 is a node and it is asymptotically stable. Now, let us consider this system dx by dt equal to 8x minus y square, dy by dt equal to minus 6y plus 6x square. So, here we have the corresponding linear system will be dx by dt equal to 8x, dy by dt equal to minus 6y. So, a equal to 8, b equal to 0, c equal to 0, d equal to minus 6. So, ad minus bc is minus 48, which is not 0, and therefore, first condition ad minus bc not equal to 0 is met. P1 xy is equal to minus y square, q1 xy is equal to 6x square. So, again P1 xy, Q1 xy are polynomials in x and y of degree 2 each. So, they have continuous first order partial derivatives. Further, as we have shown in example 1, P1 xy over under root x square plus y square, limit xy tends to 0 0, P1 xy over under root x square plus y square is equal to minus limit xy tends to 0 0, y square over under root x square plus y square, it will be 0, and similarly limit xy tends to 0 0, 6x square which is q1 xy upon under root x square plus y square will be 0. So, the second condition is also met. Now, let us see the characteristic equation is lambda square minus a plus d into lambda plus ad minus bc not equal to 0 is equal to 0. So, lambda square minus a plus d, a is equal to 8, d is equal to minus 6. So, we have lambda square minus 8 minus 6. So, we have 2 lambda, lambda square minus 2 lambda, and ad equal to minus 48. So, we have lambda square minus 8 lambda plus 6 lambda minus 48 equal to 0, and this gives us lambda minus 8 into lambda plus 6 equal to 0. So, the eigenvalues are lambda equal to 8 and minus 6. Now, the eigenvalues are real, unequal and of opposite sign. So, the point 0 0, let us go to the theorem. If lambda 1 and lambda 2 are real, unequal and of opposite signs, then the critical point 0 0 is a saddle point. So, it is a saddle point, 0 0 is a saddle point. Okay. Now, we go to regarding stability. Regarding stability, see, we have, if the critical point 0 0 is asymptotically stable, then the critical point 0 0 of 2 is also asymptotically stable. Okay, here if either lambda 1 or lambda 2 is real and positive, or they have conjugate complex, or they are conjugate complex with positive real part, that then not only 0 0 is an unstable point of 3, but also 0 0 is an unstable critical point of 2. So, here we have seen lambda 1 is equal to 8, lambda 2 equal to minus 6. So, one of the two eigenvalues is positive, real and positive, and therefore, 0 0 is a critical unstable point of 2, unstable point of this equation system. So, this is unstable. Now, let us find other critical point, a real critical point of this system. Okay. We have seen dx by dt equal to 8x minus y square, dy by dt equal to minus 6y plus 6x square. So, we have only considered the real critical point 0 0, but it has other real critical points also. Let us find those other real critical points and see what are the what is the nature of the critical point there. So, for that, as we know, the critical points of a system is given by dx by dt equal to px by, dy by dt equal to qx by, px by equal to 0, qx by equal to 0. So, we shall have 8x minus y square equal to 0 and minus 6y plus 6x square equal to 0. So, this will give you y square equal to 8x and here x square equal to y. So, we have here this will give you by 4 equal to 64 x square, by 4 equal to 64 x square is by, so 64 y. So, we have y times by cube minus 64 equal to 0. So, this is by into by minus 4 and then by square, this is by cube minus 4 cube. So, by minus 4 by square plus 4y plus 4 square. So, 16 equal to 0. Now, the real solutions of this equation you can see are by equal to 0 and by is equal to 4. This equation by square plus 4 by equal plus 16 does not give us real solution, because b square minus 4ac is equal to 16 minus 4 into 1 into 16, which is negative. So, by square plus 4 by plus 16 does not give us a real value of by. The real values of y are 0 and 4, and x square is equal to y. So, x square equal to by 0. So, or we can find okay. So, x square is equal to by. So, x is equal to 0 when by is 0 and x square is equal to 4 when by is 4. Now, this gives you two values of x is equal to 2 and x is equal to minus 2. Let us see x is equal to 2. If you take x equal to 2, then y square is equal to 16 is fine. Okay. So, x equal to 2 is admissible, but x equal to minus 2 is not admissible, because y square becomes minus 16. So, corresponding to 4, x should be taken as 2. So, we have two real critical points are 0 0 and 2 4. Now, the nature of the critical point 0 0 we have already found. So, let us see the nature of the other real critical point 2 4. So, we have x equal to 2, y equal to 4. Let us translate this point 2 4 to 0 0 by putting y equal to x minus 2 and eta equal to y minus 4. Then this x equal to 2, y equal to 4 will go to y eta plane at the point 0 0. Now, let us write the given equations in the form of xi and eta. So, we have dx by dt equal to 8x minus y square, dx by dt equal to 8x minus y square, and dy by dt equal to minus 6y plus 6x square. Okay. Now, you can see here d xi by dt equal to dx by dt. So, we have d xi by dt equal to 8x. So, 8 times x equal to xi plus 2 minus y square is eta plus 4 whole square. So, we have 8 xi plus 16 and we have minus eta square minus 8 eta plus minus 16. So, we get this d xi by dt equal to 8 xi minus 8 eta minus eta square, and d eta by dt, d eta by dt is equal to dy by dt. Okay. So, dy by dt we can write as d eta by dt, and then minus 6 times y is equal to eta plus 4 plus 6 times x square xi plus 2 whole square. So, we get minus 6 eta minus 24, and here we have 6 xi square and we have 4 xi. So, 24 xi and then 4 into 6 24. So, this cancels with this, and we have 24 xi minus 6 eta, and we have 24 xi minus 6 eta and plus 6 xi square. Now, you can see d xi by dt is equal to 8 xi minus 8 eta minus eta square, d eta by dt is equal to 24 xi minus 6 eta plus 6 xi square. This system is of the same type as we have taken dx by dt equal to ax plus by plus p1 xy, and dy by dt equal to cx plus dy plus q1 xy. This system is same as this system. You can see AD minus BC is not equal to 0. Here we have A equal to 8, B equal to minus 8, C is equal to 24 and D is equal to minus 6. So, AD is minus 48, AD minus BC will be minus 40 plus 24 into 8. So, that will be 192. So, this is not 0, and you can see P1 xi, P1 x by is P1 actually xi eta here, P1 xi eta is equal to we have minus eta square, and P1 Q1 xi eta is equal to 6 xi square. So, P1 xi eta over under root xi square plus eta square as xi eta goes to 0, 0 is 0. Similarly, Q1 xi eta over under root xi square plus eta square goes to 0, 0, 0 as xi eta goes to 0, 0. So, both condition 1 and 2 are met, and therefore, the solution of this system, the critical point of this system d xi by dt d eta by dt, that is 0, 0 in xi eta plane, will be same as the corresponding linear system. the eigenvalues here for this system are we have 8, so lambda minus 8, sorry, we have 8 xi minus 8 eta, so 8 minus lambda minus 8, and we have here 24, and we have here minus 6 equal to 0. So, we have to find eigenvalues here. We have 8 minus lambda, then minus 8, 24 minus 6 minus lambda. So, we will get here 8 minus lambda into minus 6 minus lambda, and then we have here plus 192 equal to 0. Okay. So, what equation we are getting? Minus 48 plus 6 lambda minus 8 lambda and then plus lambda square plus 192 equal to 0. Is it okay? Minus 48 plus 6 lambda minus 8 lambda plus lambda square plus 192. So, lambda square minus 2 lambda, lambda square minus 2 lambda, 192 minus 48. equal to 0. Now, b square minus 4 ac is negative here. So, it will give you complex roots, lambda equal to 2 plus minus under root 4 minus 4 into 144 divided by 2. Okay. So, it will give you 1 plus minus I times 2. Here what we will get? We can take 4 common. So, we will get 2 here and then under root 143. So, this 2 will cancel and we will get 1 plus minus I square root 143. So, 2 eigenvalues are conjugate complex alpha plus minus I beta, alpha is positive, it is 1. So, we can see the nature point. Okay. So, in this case let us go to this one, theorem 1. If lambda 1 and lambda 2 are conjugate complex, but not purely imaginary, since alpha is equal to 1, they are alpha 1 alpha 2 are not purely imaginary, then the critical point 0 0 is a saddle point. So, 0 0 in the xi eta plane is a saddle point, this 0 0 in the xi eta plane, 2 4 has gone to 0 0 in the xi eta plane. So, it is a spiral point. If lambda 1 and lambda 2 are conjugate complex, but not purely imaginary, then the critical point is a spiral point. 0 then 0 0 is a spiral point. So, 2 4 is a spiral point, and regarding stability, if either lambda 1 and lambda 2 is real or positive and are they are conjugate complex with positive real parts, then not only 0 0 is an unstable point of 3, but also it is unstable critical point of 2. So, 0 0, so 2 4 or you can say 0 0 in the xi eta plane is a unstable point. So, it is unstable spiral point. Now, let us come back to the xy plane. 0 0 is the point in the xi eta plane, but in the xy plane it is 2 4. So, the nature of 2 4 is that it is a unstable spiral point. Thank you very much for your attention.